Welcome to the last session of CoqPL or RockPL. Without further ado, this is our first presenter, Prasita. So she will be talking about verifying C programs and synthesis using LLM.
Okay, thanks for the introduction. So I'm Prasita. We are here to talk about SYNVER towards automated verification of LLM-synthesized C programs. This is joint work with my advisor, Ben Delaware from Purdue University. So to start with, the keynote on Wednesday presented an appropriate picture of the present scenario of program synthesis. On one end of the spectrum, you have these deductive synthesizers that produce programs with strong guarantees, but they're not that expressive. And on the other end of the spectrum, you have these LLMs, large language models, which are black boxes, and they would, owing to the large search space, they would always produce a program or a set of programs given a specification. So what we tend to do in this work is we tend to elevate the guarantees of an LLM-generated programs by incorporating a foundational verifier. So we present a general-purpose synthesizer in the form of LLMs, which accept a diverse set of specifications, ranging from separation logic to API calls. And given the specification, it generates a program, which is then subject to verification. And we use foundational verifiers like Rock or Coq in this case to reason about their correctness. Now, as we said, LLMs have large search space, so it is always going to produce some output. And since we are subjecting it to a diverse set of specification that is expressed in a rich logic, we use foundational verifiers to reason about their guarantees, and there is a significant verification effort needed. There have been works like Suslik and Cobalt. Suslik tackles synthesis of heap manipulating programs, and Cobalt tackles synthesis of API programs, but then they're again standalone synthesizers. They're not as general purpose as we achieve in this work. So the goal of SYNVER here is to, again, reason about the full functional correctness of programs generated by LLMs, and we do this by incorporating automation inside Coq and with the help of some user assistants. So this verification comes with a set of challenges. This is too good to be true. So given a hot triple PCQ, where C is the program that is synthesized by LLM, we use VST and incorporate some automation on top of it to verify the C program generated. But given the automation, since this is a very rich set of specifications we are dealing with, it can produce a set of unresolved goals. And these unresolved goals can be in the form of either the automation is not strong enough to discharge them, or the program generated is incorrect. So in this work, we tend to eliminate the set of unresolved goals to the minimum by either completely automating the whole proof or minimizing the set of unresolved goals. And we do this by incorporating certain biases in the search space. So let's look at a demo. Oh, OK, I have it. All right, so here it asks us to enter the specification and separation logic. We are trying to append a list. Then the function name followed by the function signature, and then the English description of the function. Then it asks for a couple of input-output examples. This is how our prompt design works. We provide the first one, the second one, and then it asks us to provide the name of the specification file. We provide everything, and we see there's a program that is synthesized, and this is generated by the LLM. Now, if you look at it, we will see that it does indeed generate the correct program for appending to lists. And we see that what we observe in the output, and I will be highlighting you, is that SYNVER is able to completely automate this proof. So it says that it's successfully verified against this specification. So now let's look at another example where it may not be able to automate it completely. So this is another example which will try to delete the first element of the list, of a single linked list if possible. So I'm not going to walk you through all the details. We enter all of them again, and we see that there is a code synthesized, and this code is correct on examination. But it says that it cannot completely automate the proof. It does generate some error files, some side conditions. And we look at the side conditions. We examine the error file. We see that it's unable to resolve an entailment. And this is a single linked list. So on inspection, we see that the two lists on the left and right-hand side need to be equal. And then the user can manually walk through the specification file and look at the partial proof generated. And we see that this is the sub-goal that it failed to automate, and the user will assert and prove the equality of the left and right-hand side list, and then they're going to perform the rewrite, and then entailer is going to take care of it. So this is how we discharge the proof when sub-goals are discharged, not able to automate. So we present the outline. So SYNVER is a general purpose synthesizer for C programs. We generate easily verifiable code through prompt design. We propose a verifier called StepAuto, which is an LTAC on top of VST to automate proofs that are generated in this fashion. For programs generated in this fashion, we conclude with the experimental setup and results. So now we present the workflow of SYNVER. So there's the LLM, the specification, and the biases. It will generate a program which is subject to syntax and bias check. Until the checks are done, it's going to do a to and fro with the LLM. Once it is syntax checked and bias checked, that program is then fed to StepAuto, which then either completely automatically proves the goal or involves the proxy, which is user here, to either discharge the proof, or it's unable to discharge the proof, which means the program is incorrect, and then the user appropriately reprompts the LLM. So now, natural question is, why do we need to incorporate these biases, and what are they? So our goal here is to generate programs that are easier to verify, easier to automated verification, so which is why we incorporate these biases. And what we observe is that we would not want to infer novel specification and then verifying them, because inferring novel specification is non-trivial, and that requires extra verification on top of it. So if we can somehow eliminate this with alternatives, that would be a good option for programs in this space. So what we say is that we say no to loops and yes to recursion, and we give it a set of novel helper functions, and we only ask to use those helper functions, to not infer any novel helper function. So if you take a look at the workflow, this is the first part where, let's say it passes the syntax check. So in the LLM, we say that recursion please and only call function given. And if it doesn't follow the biases, we reject them and keep reprompting until the program is generated in the correct shape. So here we meet our objective of no specification inference. Now, the second part is this is not related to the biases, but we tend to write specifications that are automation friendly. Now, VST comes with a set of very advanced tactics and algorithms. One of them is list solve, wherein we observe that writing specification with predicates like for all 2, and instead of like inlining them like writing a spec for ascending order, writing specifications using predicate and expressing the relation of pairwise elements would help automate it better. So we tend to write specifications that are automation friendly. Now, once the biases are checked, we feed the program to StepAuto for verification. So now I'm going to do a walkthrough of how StepAuto works. So StepAuto works in a similar fashion to VST, that is, it does forward symbolic execution. So this is the part that I want to focus on, where you have generated a program that is bias correct and syntax correct. So once what StepAuto is equipped with is a set of data structure, hint lemmas, and it does shape analysis. So it uses the VST Floyd tactic forward to keep doing forward symbolic execution until it's stuck at a state. And then it examines the stuck state. The state can be a Haut triple or a non-Haut triple, and it does certain automation tactics based on the shape of the goal. So let's look at certain cases. So the first step is the if statements. If there's an if then else statement, which is followed by another statement, so here D follows the entire if then else block. Here, VST uses a tactic called forward if to drive the symbolic execution forward. But if there is a statement following the if then else, it would require a joint post condition. A joint post condition is nothing but the specification of the 2 branches, but we don't want to do specification inference. So what we do is we transform the goal, and by pushing E into both the then and the else block. So once we transform the program, forward if is then able to automatically discharge the next step without requiring specification. So in this way, by transforming the goal, we avoid inferring specifications. The next part is function calls. Now, function calls are really important in our paradigm because we deal with recursion and we also deal with API calls. VST has a tactic here, forward call, to drive the proof, which requires parameters of the function call. Now, this is quite non-trivial, and it often fails to infer the correct set of parameters. So we do have a tactic for parameter inference. I'm not going to go into the details of the tactic, but if it is inferring correctly, it's not guaranteed to infer correctly. If it infers correctly, then we move forward. Otherwise, the user is involved to provide the parameters and make progress. But in spite of all of this, querying the relevant proofs, hint lemmas, it may still fail to make progress. In that case, also, we do need assistance from the user, where they can either resolve the goal or may just reject the program, telling the LLM that this is the incorrect program. So for non-hot triples as well, we perform a similar kind of automation structure. So it looks at the shape of the goal. It can be an entailment, inequality, et cetera, and it would fire the respective tactics. So VST is already equipped with a rich set of tactics like entailer for entailment, LIA, list solve, et cetera. If it's discharging the proof, well and good. Otherwise, it looks at its hint lemmas, tries to discharge the goal. If it can't, then again, the user is involved. So now we've presented the outline of what SYNVER looks like. So now we go to the experimental setup and present results of what it can actually do. OK. So here in the experimental setup, we have a benchmark of 50 programs, and we split across basic, which comprises of arrays and basic variables, separation logic, which comprises of heap manipulating programs and API calls. We don't propose this benchmark. These are a set of programs that are borrowed from the synthesis community. We do support multiple types for the programs. So all the programs are supported with integer types. We also have support for strings and very limited support for double to automate the proofs. We use GPT-4o as the LLM, and it is prompted with the components as we described, along with the biases. So now in our results, we see that GPT was able to produce the correct code for almost all the programs but one. And it did incorrectly generate the code for one case, which I'm going to talk about, which is this generate skewed BST. So what it says is, given a list of n keys, generate a skewed BST. And given the description of the prompt, it's unable to parse. So what the user comes in and says is, I'm giving you the definition of what a skewed BST is. In spite of giving the definition, it still fails to produce the correct code. Then the user says that you have to sort the array in ascending order and then insert the keys one by one. So basically, we give the whole algorithm, and then it's able to generate the correct program in this case. Now, coming to the results, so SEP-Auto is able to, the automation results, is able to mostly automatically verify the set of benchmarks, but it does generate side condition, and it's not complete. The side conditions, as we highlighted a couple of them, and we'll be looking at some examples as well. First odd and BST min node, like first odd, the specification has nested quantifiers, which is difficult to automate, and BST min node requires the magic wand of the separating implication operator, which is also difficult to automate. Now we evaluate our results by posing certain research questions. The first question is about the biases. So remember, we talked about the biases that we don't want loops, we want recursion, and we don't want it to synthesize novel helper functions. So what we want to ask is, if we don't provide the biases in the prompt, what kind of programs will it generate? Will it generate automation-friendly programs or not? So we reran experiments, and what we found out was, of the 26 programs that required recursion, 24 of them were generated with loops. So it naturally tends to emit programs with loops and not recursion. For helper functions, they typically don't tend to synthesize novel helpers, but for one of the examples, isEven, we found that it synthesized a function called isOdd and tried to verify it, which was not present in the set of function calls given. Now, I would like to walk through some of the cases where SEP-Auto may fail. So this is one case where it fails. So basically, there are two indices, IND and VRET. It fails to infer the relation between IND and VRET, and we need to destruct it with the appropriate inequality. Since it fails to realize this, it gives up, and then the user destructs it. We have multiple subgoals, which is then automated by SEP-Auto using the hint lemma sublist split by taking into account this hypothesis. Then the second one, as we saw in the demo, is we have an entailment on the left and right side. It's a singly linked list that ends at null. It's not a segment. And it starts at the same address, so which means that both left and right-hand side, they represent the same list. But it is unable to pose and prove this premise. So in this case also, it gives up, and the user proves it, as we saw. Then the third case, as I talked about, automation is supported. It's very limited for the magic wand operator, and it does need user assistance in this case. Now we extend this research question by analyzing the failure mode of SEP-Auto versus other verifiers. We do comparison with Pharmacy, Verifast, and RefineC. Now Pharmacy, it's very good for the basic category of programs, but when programs require dynamic memory allocation, or when it involves separation logic conjuncts, it requires a lot of annotation burden, which is very difficult to infer. Verifast is, again, more expressive than Pharmacy, but it's, again, automated. So in Verifast, for example, there's a program that is synthesized correctly with Verifast, but you may need to insert annotations in between. And if you don't insert it correctly, this is the correct program, it would say the error message in the verbose mode is that it's unable to verify the correct post condition and alongside the SMT queries. And as per my experience, it doesn't give a concrete set of goals as to what went wrong. And I can infer whether I have to write a lemma or annotation or what. Refined C, on the other hand, is both automated and foundational, so it's very expressive. It has good automation support for the WAND operator as well. But along with the annotated specification, it does require support for certain hint lemmas or tactics for the proofs to go through. So do a fair evaluation. We commented out the helper tactics if you're not able to synthesize, but we found out that in this case, it does. If it's not able to do the whole proof, it generates the unresolved goals. And these unresolved goals are of the nature which SEP Auto can discharge. So what we found out was SEP Auto's automation can be fed into other foundational verifiers like Refined C to discharge their unresolved subgoals. So the last question we pose is, do the components of the prompt matter? So we saw that the prompt has a bunch of components. So how much does each component of the prompt contribute to generating the correct program and the desired program? So the first rank is the biases. We saw that if we don't give the biases, it would tend to emit programs with loops, mostly. And then the English description, then followed by the meaningful function name, which is also in English. Then the formal specification, and input-output examples are basically don't cares. We didn't find them effective. So we evaluate this by doing certain ablation studies of the prompts. So this is a specification which is saying that you want to return another list, which is using the filter function. So you don't want to change the list. You want to create another list and return the head of the list. And over here, we don't give any English description. There's a mathematical description and the biases. So what we see is there is a program synthesized, but it's not quite correct. It's modifying the list. So this led us to conclude that maybe LLMs don't have a good understanding of the separation conjunction operators. And on running our benchmarks, we found out that only 12 out of 23 programs in the separation logic benchmarks were generated correctly. To further solidify our claims, the next ablation that we conducted was we gave a proper English, a very descriptive name, but we didn't give the natural language specification of the same function. And it did generate the correct program. And the final result was it was able to verify 20, which is an improvement from 12 in the separation logic constructs. So to conclude, LLMs with foundational verifiers giving guarantees can be used as a general purpose synthesizer. LLMs have a large search space, and since C is a very mainstream language, it is well trained on C, so it gives us correct programs following the biases. It does respond positively to biases, and the automation is well suited. SEP Auto is, again, not complete. It can generate a set of unresolved goals where we need user assistance at the moment. But yes, it is very possible that there might have been a data leak, because of which we observed that it was generating correct programs for almost all of the programs in one try. So in the current state right now, what we have in this framework is, with some automation on top of Coq and user assistance, we are able to reason about full functional correctness for the programs that are generated correctly. What we want to achieve is that right now, with the automation support and no user support, it's able to automate a bunch of the proofs, but it's not quite out there. So what we want to do is minimize the assistance of user in the loop for now. And what we are immediately looking at is giving the unresolved goals to LLM and examining how much they can discharge the proofs and how much we can do by just having LLMs discharge the whole thing instead of having users. We want to minimize user involvement, and also we are looking into automating the WAND operator and working on other automation aspects where SEP Auto fails. Okay, so this is the end of my talk, and with that, I'll be happy to take questions. Thank you.
We have time for a few questions. Yes?
Really amazing talk. I have a question about the prompting part. So I'm curious to know how sensitive it is to prompts, and is there any specific structure or way that you have to prompt to get the right solution or to guide the LLM towards?
Yeah, good question. So what we found out, as I said, it's very sensitive to the natural language description. So if that is not correct, we found that it's not quite generating the correct code. So the English description needs to be absolutely on point. The input-output examples we found out where it was not affecting, but the proper English description of the specification needs to be there along with the biases, which are also described in English.
So what do you mean by proper English description?
So you eliminate ambiguity as much as possible. That's what,
okay.
Yeah.
Okay.
So when I'm talking about filtering a list, I would say that you make a copy and return the pointer to that list and not, sort of modify that list, something like that.
Okay, in a way, like you're kind of giving it informal description.
Right. Yeah.
Thank you.
We have time for one more question.
This is too good to be true. So I want to know, like, how were the specifications provided? Were they in natural language or some formal language?
Yeah, so they were both formal specifications were provided as well as natural language specifications were provided. So both of them were provided.
Both of them, you should have both of them, right?
In the prompt, we have both of them, but in our ablations, we kind of concluded that it is more like it listens to more of the English description to generate the correct program.
Is the recursion like multifunction, or a function can only calls itself?
Right now, it is only calling itself. Right now, our benchmarks don't have mutually recursive call, if that's what you're asking. Our benchmarks don't have that, but I believe it can support it. But yeah, our benchmarks don't have that. Yeah.
And one very short question. If you don't like loops and like recursion, why not a simpler, I don't know, functional language? Why C? Is it because
C is a mainstream language? We want to assess the ability of LLMs to generate in a mainstream language like C and argue the full functional correctness of it, rather than that's.
Thank you.
Okay. I guess we can ask one more quick question. You want to ask a question, right?
Just a quick clarification.
Yeah, and maybe you can ask while setting up your talk.
So you mentioned that data leakage might affect the results, and I don't know what data leakage is, so if you could explain.
Yeah, so it might have been possible that the LLM has already seen that program, so it was generating it correctly in one shot. Thank you.